Dears, have a nice time. Today we will deal with the topic triple integrals in cylindrical and spherical coordinates. First topic, triple integrals in cylindrical coordinates. Before coming to the topic, let me introduce what you meant by a cylindrical coordinate system. Cylindrical and spherical coordinates are two coordinate systems which can be used to represent a point in the three-dimensional space. You know the Cartesian coordinate system of representing a point in space in the form x, y, z. Similarly, r, theta, z is another representation of the point in cylindrical coordinate system. Now let us check how the point r, theta, z uniquely determines this point. First of all, you draw a perpendicular from the point to the xy plane. And the distance of this point from the origin is r, and the angle made by this line with the x-axis is the angle theta. It is actually similar to our polar coordinate system. And z is the perpendicular distance of the starting point to the xy plane. So in that way, we can uniquely determine this point r, theta, z. Now, how can you convert a point in Cartesian coordinate system to the cylindrical coordinate system? You can very easily form these formulae. X is equal to r cos theta, y equal to r sin theta, and z equal to z itself. Because this angle is theta here, and this distance is actually x, this distance y, and the perpendicular distance z. So cos theta is adjacent side by hypotenuse, that is x by r, or x equal to r cos theta. Similarly, sin theta is y by r, or y equal to r sin theta. In using these formulae, we can convert a point in Cartesian coordinate system to the corresponding cylindrical coordinate system. Today we will consider triple integrals in cylindrical coordinates. Theorem. Let G be a solid region whose upper surface has the equation z equal to g2 of r theta and whose lower surface has the equation z equal to g1 of r theta in cylindrical coordinates. If the projection of the solid on the xy plane is a simple polar region r, and if f of r theta z is continuous on G, then this result happens. Triple integral over G, f of r theta z dv equal to double integral over r, integral from G1 to G2, f of r theta z dz dA, where the double integral over r is evaluated in polar coordinates. Let me explain the result now. Suppose you have a solid here G, and you have to triple integrate over the region G of the function f of r theta z. Now how can you locate the limits of the triple integral? Here you may see that to get the limits of z, we consider a perpendicular line from the first region, the region in the lower portion, to the region in the upper portion. Along this perpendicular line, z varies from g1 of r theta to g2 of r theta. So that are the limits of z here. Now how can we find the limits of r and theta? So we are taking the projection of this solid in the xy plane, and now in the xy plane we consider the limits of r and theta just like in the polar coordinate system. And here you know r varies from r1 theta to r2 theta, and theta varies from here theta 1 to theta 2. And also you know double integral over r dA is actually replaced by integral over theta, integral over r dr d theta. So this integral is evaluated this way. Triple integral over G, f of r theta z dv equal to integral over theta, integral over r, and integral from G1 to G2, f of r theta z r dz dr d theta. So let us go through a problem. Use triple integration in cylindrical coordinates to find the volume of the solid G that is bounded above by the hemisphere z equal to root of 25 minus x square minus y square, below by the xy plane, and laterally by the cylinder x square plus y square equal to 9. Now what's the equation here? Z equal to square root of 25 minus x square minus y square. if you take the square root on both sides, you have actually z square is equal to 25 minus x square minus y square, or you have x square plus y square plus z square is equal to 25. You know this is the equation of a sphere. But here we are considering only the hemisphere, that is only the positive part of z. For that we are taking z equal to square root of. So since it is taken as square root of this one, we are considering only the positive values of z. That is, you are considering the upper hemisphere. So this part is the upper hemisphere, and the lateral part is a cylinder. Now the lower part is the xy plane. That is our solid G here. We are asked to find the volume of this solid. Volume of the solid means V equal to triple integral over G dV. In Cartesian coordinate system, you know it is triple integral over G dx, dy, dz. So we are taking the dz as itself. Now we have to find double integral over R dA. It is actually double integral over R dr d theta. So that is replaced here. dA is replaced as R dr d theta, and dz is here. Okay, now we have to locate the limits of z, r and theta. How can you find the limits of z? For that, we are considering the lower part and the upper part of the solid. Here it is given that the solid is bounded above by this hemisphere. So our upper limit is z equal to this one, root of 25 minus x square minus y square. And you know x square plus y square is r square. So you have root of 25 minus r square. That is the upper limit. And the lower limit is actually the xy plane, that is z equal to 0. So you have the limits of z here, 0 to root of 25 minus r square. Now how can we find the limits of r and theta? For that, you have to take the projection of this solid on the xy plane, and you know the projection is itself the lower part of the solid here, that is x square plus y square is equal to 9. That is a circle. And here in the circle, r varies from 0 to 3. This is a circle with radius 3, because here you have x square plus y square equal to 3 square. Okay, therefore r varies from 0 to 3, and theta varies from 0 to 2 pi. So you have the limits of r as 0 to 3 and the limits of theta as 0 to 2 pi. Now you just integrate. Find the integral with respect to z first. So you have r into z between limit z equal to 0 to root of 25 minus r square. Now you have this result. Now substitute 25 minus r square as some u. Okay, so you have minus 2r dr equal to du, or you have r dr is equal to minus 1 by 2 du. Therefore integral r into root of 25 minus r square dr, it's equal to integral root u into minus 1 by 2 du. Root u integral is u raised to 3 by 2 whole divided by 3 by 2 into minus 1 by 2 is the. So altogether you have minus 1 by 3. U is 25 minus r square. So 25 minus r square raised to 3 by 2. Between limits 0 to 3. So you have r equal to 0 to 3. Apply the limits and complete the integration. You will get 122 by 3 pi. So this is the volume of the solid G here. Now let us have another problem. Use cylindrical coordinates to evaluate this triple integral. Here the triple integral is given in Cartesian coordinate system. You have to convert the integral to an integral in cylindrical coordinate system. The function to be integrated is x square, and you know x equal to r cos theta in cylindrical coordinate system. So replace x by r cos theta. Now we have to find the limits of z, r and theta. Here the limits of z, y and x are given. So the limits of z are here 0 to 9 minus of x square plus y square, and you know x square plus y square is r square. So you have 0 to 9 minus r square. That's the limits of z. And you know x equal to r cos theta. So replace x square with r square cos square theta. Now what will be the limits of r and theta? For that we consider the projection of the solid in the xy plane here, And here the limits of y, it is given that limits of y varies from minus root of 9 minus x square to root of 9 minus x square. And it is actually, if y is equal to root of 9 minus x square, you have y square is equal to 9 minus x square, or you have x square plus y square equal to 9. It represents a circle. And you have to find the limits of r and theta with respect to this circle in polar coordinates. And you know, for this circle, r varies from 0 to 3 and theta varies from 0 to 2 pi. Now you can do the integration in this way. In the place of x square, you have r square cos square theta. Limits of z are 0 to 9 minus r square. And limits of r are 0 to 3 and limits of theta 0 to 2 pi. And here dA is replaced by r dr d theta. So altogether you have to integrate the function r square into r. You have r cube cos square theta dz dr d theta. So first of all we will integrate with respect to dz, with respect to z. Okay. So the integral is z into r cube cos square theta, where z varies from 0 to 9 minus r square. So substituting the upper limit in the place of z, you have 9 minus r square into r cube, that is 9 r cube minus r raised to 5 cos square theta minus z equal to 0, it becomes 0. Now you have to integrate this function with respect to r. So cos square theta can be considered as a constant. Integral of 9 r cube minus r raised to 5. It is 9 r raised to 4 by 4 minus r raised to 6 by 6 into cos square theta. Between limits r equal to 0 to 3. So apply the upper limit minus lower limit. Finally you will get an integral like this. And to integrate cos square theta, you have to use the formula. Cos square theta is 1 plus cos 2 theta by 2. Again integrating, we will get 243 pi by 4. So this is a way of integrating a function in cylindrical coordinate system. So actually in the problem, we replace this dy dx with r dr d theta. Okay, and convert all the functions f of x, y, z in Cartesian coordinate system to corresponding cylindrical coordinates. Then find the limits of r and theta using the limits of y and x. We first identify the region corresponding to the limits of x and y, and we will convert it to the limits of r and theta. In this case, the limits of y and x gives you the figure x square plus y square equal to 9. And you know, along this circle, r varies from 0 to 3 and theta varies from 0 to 2 pi. So that's a method of integration in cylindrical coordinate system.